Let's get started. Good Thursday afternoon. So today we're gonna finish up goodness of fit today, and then we're gonna move on to ROC curves, which is related but not related. And so we're gonna have to talk about how goodness of fit and model discrimination are related and different. And we'll work through that, but it will be fun, I promise. So we kind of ended off last time talking about the Hosmerlemma show test, and we'll finish that up. But right before that, we were talking about this other method for conducting the goodness of fit test, which we called it was a deviance test using this thing called deviance events trials, and this basically was comparing your given model to what we called the fully parameterized model. And that was the model that had as many terms in it as you can make combinations of covariates. And the basic idea is that this fully parameterized model that had all of the effects and all of their interactions and everything is kind of the biggest model you can make in some sense. And that model always predicted the expected probabilities of the data, the actual observed kind of probabilities of the outcome in your data at each covariate pattern. So like here were the 4 covariate patterns, C equals 1, E equals 1, and then we said that the observed probability of disease was 0.6, 0.4, 0.3, and 0.7. And so that fully parameterized model always exactly, it estimated these perfectly. And so this thing called the deviance events trials measured the departure from this, the model that has all the possible interactions. And so this model does not have the E by C interaction term, and this was the test statistic value for that. We talked about how there was a chi-square test. And then we also said that, well, actually, you can't use that model if you have a lot of covariate patterns, which happens when you have a continuous variable. So we talked about this other thing called the Hosmerlemma show test, and it takes a very different approach. It doesn't use this idea of the deviance. And what it does is it makes a very simple kind of very, bird's eye view of it takes a very bird's eye view of your model output and just says like, hey, let's look at all the predicted probabilities for every respondent or every observation in your data set. Every person, given their covariates, you can predict their probability of the outcome. Let's look at the sum of their predicted probabilities and compare it to the sum of the actual outcomes, the actual 0 ones that actually happened for those people. And on average, you'd expect that the sum of the predicted probabilities for 20 or 30 people would hopefully more or less equal the sum of their 0-1 outcomes. It may not, it's not going to nail a specific person to a specific outcome, but in general, if you have a whole bunch of people, 0.3s and 0.7s and 0.4s, you sum up all of their probabilities, and that should hopefully sum to the number of events that was observed in that group of people. And we had this model here that had a whole bunch of predictors. It frankly doesn't matter in a sense what's in the model because we're actually just evaluating how this model did relative to the data that was observed. And we saw here that the standard way to do this test is you split the group into tenths. And so here we have about 600 people in the data set because there's about 61 people in each group. And what you see is that kind of within each row, the observed number of events, 29 out of 60, is more or less equal to the sum of the predicted probabilities for those 60 people. Some people, basically you'd imagine that their probabilities on average were about 0.5 because it's saying about half of them, 29 out of the 60 should have gotten the disease outcome. So people are bouncing around. Some are 0.4, some are 0.6, some are 0.55. But the sum of their predicted experiences more or less nails the sum of the events observed in the 60. So this is like nothing to do with deviance. This is like a really high-level view of how the model did on average relative to the observed data. And you can conduct a chi-square test on this, which we talked about, and it basically uses all of the observed minus expecteds and on the left side here, and on the right side, which is the, this is event and non-event. So this is by subtraction, frankly, the same information as on the left side, but you use both in the test statistic. And it's a chi-square with 8 degrees of freedom. This 8 is because, this 8 is actually, yeah, it just is 8 degrees of freedom. I'm just going to say that. And this is a standard kind of, usually it's done as the deciles, like this. So we kind of ended here by a form. This is just the formal definition of the method. You can make you don't have to make it a 10-row table. You could do more. You'll have to adjust the degrees of freedom to not be 10 minus 2, which is 8. You can make it however many. If you can make it a 20-row, 20. Divide the data into 20ths if you felt fancy, and it would be an 18 degree of freedom test. But it's usually 10. So okay, so that's the Hosmerlemma show test. You could, in a sense, if you really wanted to, use this to compare two models in some sense. If you imagine you have, a model, we had a model above that was basically an interaction model. It has some interaction terms. And imagine there was a reduced model in that Evans County example that had no interaction terms. You had a different model, and you were considering two candidate models. You could maybe, in some sense, use this test statistic as another piece of information about deciding what's the best model. Maybe it kind of exists outside of the framework for model selection that we've already covered in the course. But you can imagine another way, another piece of information you might use is maybe the goodness of fit statistics as well. Now here, they're both not significant, so you'd both fail to reject the null hypothesis of it's a good fit. So maybe here, I'd say maybe this is more null, it's even higher p-value or something, but I wouldn't really endorse comparing these two. But you could imagine that one of them would have really bad fit. You'd have a very significant p-value, which would say, this model does not describe the data well. So things were significant and you got statistical significance, but in general, this model does not really describe what's going on in the data set as a whole. So you can imagine this is another stream of information that you might consider. But it really exists outside of the EVW model selection world because that was all about getting the best, least biased answer for on the odds ratio. That's really a different task than this. But again, this is just like more information that you may want to also be digesting. Because at the end of the day, if you have a significant result but a model that doesn't fit the data well, you probably want to know that. But you can think about it as another piece for comparing. This is a little, we don't even have to get into this part here. This just some extra slides because I really want to get over to ROC curves. Oh, this just says what I just said here. Where does this fit in? It's honestly, this really exists outside of the framework from before. And this is all I'm saying here. And I recommend it as a final step in model selection. So really imagine you've done everything we've set up until now. You think you've got the best models. Check the goodness of fit before you report it. That's all we're saying. Because you wouldn't want to report a model that doesn't work for your data set. So model discrimination. Okay, this is a topic that's very related. And I hear a lot of flipping. Do people have this slide set? Okay, cool. So this is a topic that's, in a sense, very related. It's in this general kind of zone of does the model work for the data? Is it a good model in a general sense? Does it actually fit well? But it's going to address a slightly different aspect of what we mean by fitting the data well. And so the goodness of fit business that we were just doing was really about whether the model predicted the average experience in the data set, right? It was really does this model on average, hit like I said, the Hosmerlemma show. These 60 people, does it more or less describe what happened to these 60 people well? And with the events, trials, deviance business, it was saying, how does the model compare to the fully parameterized model, and the fully parameterized model predicted the p-hats, the probabilities, the average experience in the data set. So this is about the average experience of the people. This is about the individual experience of the people, or the frogs, or whatever you're looking at. We're in public health, we're doing people here. And so this is about individual predictions for actual responses in your data set. So, right, the model, the logistic model is a model of the probability of X. It doesn't actually model 0, 1 outcomes, right? For individual responses, those predicted probabilities are not 0, 1, they're between 0 and 1. Right? It spits out, you are this age, this weight, whatever, congratulations, 0.3, is what the logistic model is going to say. And so, but can we use the model to actually classify people into kind of high and low risk? What if you defined cut points? We're going to say everything above a prediction of 0.3 is probably going to is going to be high risk, and everyone below 3 is low risk, and it's going to actually, is going to get the disease or not going to get the disease. And this asks the question of whether you can use the model to kind of carve the data into who's going to get the event and who's not going to get the event. And the reason we care about this is because we often want to use logistic models to actually make predictions on a new set of data, right? Way back in like lecture 1, in the hazy late August days, we talked about how we kind of have two quests with modeling. Often it's about like getting the right odds ratio and like discovering the right association. And there's this other use, which is when you may actually want to use the model to predict something. There's a lot of models in medicine where we use risk score calculators. You put in some variables and outcomes. This person is at risk for hypertension or going to develop cancer or whatever it is. A lot of those are built on regression models and things that spit out predictions. And so really you may want to use your model to like talk about a person that you haven't observed yet in your data. You did your study with 1,000 people, and you may now have 1,001st person coming along, and you want to say something about their risk. And this idea of prediction as measured through the ROC curve is the way to assess how good your model is at like sorting people into those that have a high and low risk of disease. So another thing is that the goodness of fit stuff was really just about one model at a time. Like we would say, how good is our model? Like in the deviance world, it was how good is our model relative to some like idealized supermodel that's really good at fitting the data but not very practical. It was all about kind of one at a time. The ROC business can be used for comparing models. You can actually see like this model, you can like test it. Like this model predicts better than this model. And it could be another element in your model selection. You're looking again at two models, and you may want to say one's better than the other based on the ROC curves. And it's a little better set up for comparison. Now remember I showed this two Hosmerlemma show tests, and I was saying you could maybe use this as extra information. When I was saying that, was like, that wasn't actually a formal test, right? You'd say, like, this one has good fit, this one doesn't have good fit. It wasn't a formal, there's no Hosmerlemma show test to say this one fits better than this model with interaction terms is better. I was just saying you can use that as extra things to know, but there's actual formal statistical tests to compare ROC curves, which we'll talk about. So different focus. This is like, in general, how does the model do? And this is, can it be used for prediction? Does it do a good job at individual people's predictions? So to motivate that, here's just like a really basic example to show that really good fit does not imply good prediction. So here's a 2x2 table. Columns are a little flipped. SAS likes to put zeros before ones. So I'm sorry. But let's say here's your disease outcome, and here we have that this is now the unexposed, but the unexposed have a risk of 30 over 100, 0.3 over here, and the exposed have a risk of 0.5. Okay, so we would say here, okay, yeah, it looks like the 100 people that are exposed have a higher risk of the disease than the unexposed. 0.5 versus 0.3. Chi-square test says, they're associated. But when you think about it, this has a good, this model, if you fit this model, let's say this was a 2x2 table and I fit this model, alpha plus beta times exposure. Okay, this is basically the only model I can fit. I don't know imagine this is all you know. You didn't measure any other confounders. You measured 200 people and you measured, exposure and disease, and you fit this model. This model is the fully parameterized model because it's the only thing, you only measured one X variable, you fit the model to it, and it's perfect fit. Okay, so this is a perfectly fitting model by definition. Let's just say that because it has as many covariates as possible in it. There's only one, the exposure. But it's actually really, you can't actually use this model to predict who's going to get disease or not. Because if you look at it, if you look at who's exposed, half of them get, if I know that you're exposed, half of them get disease. Here we go. If I know you're exposed, I would say half of you will get disease, and if I know you're unexposed, I'd say, okay, well, a third of you, or 0.3 of you will get diseased. So it's actually, if you think about it, and this is a very hokey argument here, but this, either way, the prevalence of disease is really high, and here if I knew you were exposed, it would tell me you have a 50% chance, and here I'd say, well, you have a 30% chance, but we're going to misclassify a lot of people into disease states if all I knew about you was your exposure status, right? Knowing that someone's disease only boosts your knowledge a little bit of knowing whether someone has exposure only boosts your knowledge of whether they're going to get disease by a little bit, right? Because it's 30% or 50%, and it doesn't actually tell me much, right? Either way, the risk of disease is high. Imagine if I had some other information that would really tell me who will get disease. Either way, the prevalence is high in both groups, and knowing whether you're exposed doesn't really impart much more information. But what if there were other covariates in the population that truly parsed out some of these 80 into some people that truly have like a 1% chance of disease? What if I had to know you were exposed, but also whether you smoked and this and this and this and this, and there's really truly low-risk groups, and if I knew all of those covariates, some people are 50% and some people are actually 1% or something like that. Basically, we don't know enough to define who's truly not at risk. Everyone's, so we need more covariates to actually say something here. So this is just to show that this model will have great fit, but do a really bad job at prediction. And in fact, the area under the ROC curve, which is what this thing is 0.6, which we'll see is actually really low predictive value. So knowing exposure doesn't tell you much about disease risk here, even though there's an association. And so we can formalize this using the concepts introduced in EPI 530 around the classification table. So this is yet another one of our fun EPI 2x2 tables, but this is the one that was formalized a year ago to talk about sensitivity and specificity and positive and negative predictive value. And so just to review what this all was, right, imagine you have a 2x2 table constructed where the columns are truth, whether someone is truly a case or diseased, and on the left side, and then you have the non-case on the right side. This is kind of the truth column, what is, if you were a deity, what you would know, right? And we're not deities, and so we only know the rows, right? And we say well, our test or our observation tool, whatever it is, tells us whether someone's a case or not a case. And out there in the ether is the truth. And we use this table to assess how our tool works relative to the divine or whatever. And the sensitivity, right, is this quantity over here, which it measures, there we go, just do that. There, sensitivity. It measures how many of the truly cases are picked up by as a case by our prediction tool, right? That's what sensitivity is. How many of the cases did our thing detect? It's the true positives over the true positives plus false negatives. So this thing in the upper left cell over the column total of the cases. That's the sensitivity. And then on the other side, we got this thing called the specificity, which is how many of the truly divinely known non-cases did we say were not cases? How many of them did we correctly pick up as non-cases? So it's this lower right cell over this column, right? And then we have these other things on the rows, the positive predictive value, right? Which was how many of the, how many times when we say there's a case, how many times was it actually a case? It's kind of turning the story on its side, right? How many times when we say yay are we correct? And then the negative predictive value, which is how many of the nays did when we say no per our tool, how often was that correct? Which is this the true negative cell over the right margin here. So the deal with ROC curves is we're going to use our model as the tool. Previously when talking about classification in the EPI 530 context, it will be like, a cancer diagnostic test or, some kind of, clinical tool or, some kind of health tool that we're using to classify folks. And then we would just, then that was kind of the typical framework for talking about sensitivity and specificity. Here we're going to use the tool to mean actually what our model said about somebody, and we're going to compare it to truth, which is the observed outcome on the person. And we're going to say how well for every person does their prediction relate to their observed 0-1 outcome. Now, of course, the prediction is a probability and the truth is a 0-1 outcome, so I'll show you how we deal with that. But it's going to assess basically this for the people, each of the people in the data set. So that is what's going to go on here. So model discrimination is really going to be able to look at how well the model calls cases, and non-cases, cases, and whether it can discern who's a case and who's not a case, which is another way of saying the same thing. It's going to say, how often is it right? Is it going to correctly label the case a case and the non-case a case using the covariates on the person, right? Which is what's in the logistic regression model. So we're going to use the model to generate the predictions. And the basic idea here is that we're going to evaluate the model at different cut points in order to illustrate how good the model is. And what I mean by cut point is we're going to say somewhere between 0 and 1, we're going to make different cut points, which we're going to call these CPs. And everyone above this cut point, we're going to call a case, and everyone below it, we're going to call a non-case. So so in this example, let's say, there's some cut point here. Cut point is 0.5. Everyone that has a probability above 0.5, we're going to say, you're a case. You're going to get disease, you're going to die, or whatever it is. We're going to enumerate, we're going to make this decision rule, and everyone with who the model says is above 0.5, we're going to just predict them to be a case. Okay, and then for everyone below 0.5, we're going to predict them to be a non-case. So the model spits out this number, and then we use that and then say if 0.5 or more case. And then what we're going to do is compare the result of that process to truth. Right, which is actual observed data on the people. So we're going to say, okay, you got a 0.6 and you also were a case. So good, we correctly called you a case because your 0.6 was above 0.5. We're going to predict you to be a case, and by the way, you actually were also a case. And so that's the process. Or we might be wrong. You had the model says you're a 0.8, and by the way, you were a non-case, so the model made a bad call, made a bad decision. We're going to say that's going to go in that's going to work against us. And what we're going to do is make our kind of 2x2 classification table based on doing this for every one of the data set. So here's like a hypothetical result of this. Imagine you have 200 people, and we use a 0.5 cut point. And imagine if you had this process, so here this would indicate that 60 people were predicted as a case based on having a probability above 0.5. And by the way, they were also actually cases. But we missed 40 cases. These are 40 people that had a low probability. They were predicted to not be diseased, and we missed them, and they were actually cases. And so that would be sensitivity 0.6, because it's 60 over 100, so not very good. We missed a lot of cases with this decision rule. Okay, so that was good. That was not good. Right, so if we lowered the bar, what if we lowered the threshold and said, well, maybe everyone above a 0.4 or a 0.3 or whatever, as you lower that threshold, and I'll illustrate this, like as you lower the bar, you're going to pick up more cases. And if you remember from way back when, that comes at a cost. Your specificity suffers, if you remember that. There's a kind of this tug of war, like you win the sensitivity battle and then you lose the specificity one. So we'll get into that. But anyway, and so if you did the same thing with specificity, you'd say, okay, how many people did I predict were cases but actually weren't? That's 60 over here in this table. And this is how many people did the model say were non-cases that were truly non-cases. So that would be this 40 here. This is the specificity uses this, the numerator. So these are people with a low probability that actually were also a 0. That's good. You want to correctly call the people with low probabilities zeros, non-cases. And that's the specificity, 40 over 100. So so you would say that this, at the cut point of 0.5, the model had a sensitivity 0.6, specificity 0.4. And for the purposes of the ROC curve, which we'll get to, we also compute this thing called 1 minus specificity, which is 0.6. So it's all right. So this is crummy. This isn't good at this cut point, right? We don't like, sensitivities should not be 0.6, specificity 0.4, kind of crummy. So the deal with the ROC curve is we're going to do this at many cut points in the data set, at many cut points between 0 and 1, and the collection of that information will actually tell you how good the model is at prediction. And that's where we're getting in here. And so you need to know this information at many cut points in order to talk about your model. And what we're going to do is build it at many cut points, and we're going to make a pretty picture. That's the ROC curve. And you've probably seen these in journal articles. They come up, with relative frequency. They're used a lot in the medical literature to really talk about the performance of diagnostic tests. And it's a curve of this. That's a plot of the sensitivity by the 1 minus specificity. And each point on the plot is a result of making one such table. And so each dot, each point is going to be at a given cut point, what was the sensitivity versus the 1 minus specificity. So, for example, this 0.5 is going to correspond to there's going to be some point on the graph where there's a 0.6 and a 0.6 for sensitivity 1 minus specificity, and that would be the cut point at 0.5. And the general idea is we can use this picture and something called the area under the curve, which is going to be literally the area under the curve, surprisingly, which is going to quantify the visual by looking at the area. And so you can look at the picture, you can look at the area under it, and they're going to together tell you in a Gestalt kind of way, is this a good model for prediction? And the idea here is going to be that it says the larger the area, the better the discrimination. That's important feature A. And what that really means is when the area is high, the curve moves into the upper left. Okay, generally the curves, if it's on this line, and we'll talk more about this. If it's on this line, it's not good prediction. And the idea is that the more into the upper left it goes, the better, and the area goes up. And what that really means is that there's going to be some points out here in the upper left corner where there's very high sensitivity and very low 1 minus specificity, which means very high specificity. So if you're in this corner, it means there are cut points at which we have very good sensitivity, very good specificity. And what that means is that there's some magic cut point at which your model is awesome. Everyone above this gets disease, everyone below it doesn't get disease. The model has some theoretical cut point where it does amazingly in the population. And that might be very helpful. We'll talk about that knowing what that point is actually really helpful, because that means if you actually use that in your model, you have like a crystal ball or a magic 8 ball for your model where you say everyone that gets above a 0.6 is going to die. We know it because the model says so, or something like that. And that would be so. The more up in this corner you are, the better the better your model's doing. It has these cut points that discriminate really, really well. And we're going to walk through this. Why is it called a receiver operating characteristic curve? What the hell is that? So this is the receiver. This is in World War II early aviation thing, actually. So imagine you're in southern England in World War II, just bear with me, right? And you're using this new thing called radar, and you're trying to discern what's a German bomber versus like a bird or something else. So you had a dial that would this is a heuristic, but this is basically what you would do. You have a monochrome screen, and it's showing dots, and you're increasing the contrast of the dots, right? And things are emerging. It's like a photocopy kind of, and you're trying to discern like where the threshold is that determines like bird from plane, and you're trying to find the cut point that correctly classifies objects as the enemy versus not the enemy. And these curves were constructed to figure out the threshold on the technology side of like what's friendly and not friendly. And so this became a metric for measuring radar technology. I'm not sure if it was in England. I'm just throwing that out there. It seems like the plausible place to figure this out. But that's why it's called receiver. It's actually like a receive, like someone operating a radar terminal. They were called receivers, I guess. And these curves were used to evaluate the performance of radar systems. So anyway, now, and it leaked into public health somewhere in the last 70 years, and really in the last 30 to 40 years. So that's why it's got this goofy name. And it finds great application in things that we're interested in with the logistic regression model. And so here's one possible scenario here. Here's the model, and it performs like this. At a cut point of 1, this model has some covariates. I don't care what they are. There's some covariates in your model. At a cut point of 1, nobody is above 1. So it predicts 0 cases, okay? Remember, the cut point of 1. No one's above 1, 0 cases. Everyone's a non-case. Everyone's below 1. Okay, so this is one extreme of the curve that we're going to build, right? It has a 0 sensitivity and a 100 or 100% specificity, right? It misses all the cases because it never says there's a case, and it says it gets all the non-cases because it says everyone's a non-case. Totally uninteresting. On the other hand, on the 0 cut point, you see the same thing. This is the model that says everyone's a case, everyone's going to die, everyone's above 0. So it gets all the cases, and it also gets all of the non-cases wrong because it says everyone who's not a case is a case. Useless, but this is the end points of the curve. And now let's look at what happens in the middle. So here, at a cut point of 0.75, suddenly the model finds 10 people it finds 10 people who are above 0.75, and it calls them a case, and it turns out they actually were all cases. Okay, cool. And all of the non-cases have probabilities predicted below 0.75, so that's good. Did a good job. So at this cut point, it has a good specificity, but it only got 10 of the cases, so that's not so good, right? It still missed 90. But so it got 10 and on one side, and then here we go. We got, 100. All the non-cases were non-cases. Now let's like move the threshold down to 0.5. At 0.5, okay, suddenly there's another 50 cases discovered because they had probabilities predicted between 0.5 and 0.75. So you move down, you're like, imagine this little like meter thing in your head, and it's moving down the bar, and between 0.75 and 0.5 we discover another 50. Sensitivity goes up, yay, to 0.6. Now it's starting to feel like the model's useful. And by the way, the specificity was still at 100%. So all of the non-cases were still predicted to have low probabilities of disease. So the model's doing a good job. And now check this out. At this cut point of 0.25, we're in this cool like gray zone where all the cases had probabilities predicted by the model as to be above 0.25. Because look at this, bam, this is telling us that all of the cases were called cases. And look at this, all of the non-cases had sufficiently low probabilities. They had probabilities below 0.25, and they're all called non-cases. So here we have a point where sensitivity is 100% and specificity is 100%. It found this magical split of people where it knows exactly who's a case and who's not a case. Okay? This is awesome. This is a really good cut point. It splits the data perfectly into 2 groups. This is your magic 8-ball. And so you can make a picture. Do we have a picture? Here we go. Here's a picture of what that curve looks like. If we actually plotted all of the output of those rectangles, you would get this. All right, we're going to talk about this. This is the not good case. You would get this, in this ideal world, there's a point up in that corner where it was 100% sensitivity, and 100% specificity, i.e. 1 minus specificity 0. Your model is awesome. It's really good. It actually has a way to classify people perfectly into disease and non-disease states. So it's a good model for prediction. And it has an area of 1. You can say, what's the point? You might want to ask the computer, hey, what point is this? And it would tell you it was 0.25. And I'll show you how to do that. You can compare that to this other thing called Model 2, which was the same, let's say it's the same data, but you fit different covariates, and those covariates result in a lousy model. And that model, if you follow this through, never quite works out so well. If you follow this through, so the 0 and 1 points are the same, and you move the bar down to 0.75, and you get 10 cases, okay, that's good. But also, it falsely calls non-cases cases. Uh-oh. So it moves 10 out of here. So it did 10 good things and 10 not so good things. It moved non-cases and called them cases by accident. And so the sensitivity went up, but the specificity started to go down. It went to 0.9. And now at the next cut point, look at this. Okay, well, let's go down to 0.25. Now we've called 80 of the 100 cases, but we also made a mistake and we called 80 non-cases cases. So basically the model stinks. Every time it does something good, it does something bad, or something. So it never quite gets off the ground, really, in terms of finding like that sweet spot where it actually can make a good prediction. And what happens is here you get a picture like this. 1's going up, sensitivity is going up, and the specificity is plummeting. And it makes a picture that looks like this, if you plot it. Okay? And this picture sits on this line, on the identity line, the y equals x kind of line. And what it means, at any given cut point, the sensitivity and the 1 minus specificity are the same, if you compute this out. Okay? And what that means is your model doesn't know. It is basically a coin toss machine. It makes a bad prediction. It's just as likely to call something a case as it is a non-case. It's all it is, right? So you've invented a coin. And so and in this model, you may have had like really significant odds ratios and really unbiased, wonderful, precise, all that jazz, but actually you may be very close to this on the prediction side. So it found significant associations and maybe describes a true phenomenon, but it can't actually place a given person as high or low risk. And so again, it's about thinking about the odds ratio is like in average across the data set. Is there this is there this relationship? And that might be true, and you may have found a real significant association, but it did a really bad job at pinning a specific person as someone who's going to live or die or healthy or sick or whatever your outcome is. So this can happen too, and these could be the same data sets, but different covariates. Some covariates are super informative for prediction, and some just stink. And this is this could literally be different covariates on the same data set. And so I went over a few slides that basically say that write out what the intuition that we've been developing here. But the basic idea is that if the sensitivity is going up at the same rate that the specificity is going down, then you're on the line here. You're on this line. You can't win on sensitivity at the same rate that you lose at specificity. You're never going to get a good prediction out of that. On the other hand, if there's these kind of sweet spots where the model does really good on case detection and really good on case ruling out, i.e. specificity, then you're in this zone here. So that's kind of the conceptual idea, and then we're going to kind of talk about how you might want to do this in life, because this is all cheesy PowerPoint graphics, but we actually have a way to do this with data in SAS. Any conceptual questions on this? Yes?
Are the cut points equal to that or equal or just greater? Like, is it equal to 75 and greater?
I believe it's inclusive. It should be inclusive. I think it's greater than or equal to. Is it inconsistent? Should be greater than or equal to. Oh, maybe it's less than. Oh, you have to confirm. I thought it was actually greater than or equal to. In practice, you'll never actually get on the equal to because the model's going to go out to like 100. I mean, the predictions under the hood are out to like 30 decimal points. So you're never actually on the cut point, so it de facto never matters. Because SAS is going to be way more preciser. I'm sorry. Oh, man. It's late. It's Thursday. This is a general kind of schematic of the types of curves you might get and the AUCs that they correspond to. So if you're on the line, the area under the curve is equal to 0.5. Why is that? Oh, this is a square, and it's a 1 by 1 square, and the area of the square is 1, so half of the area is 0.5. Okay, so if you're on the triangle, here the area is 0.5, okay? So that's AUC, area under curve equals 0.5. This has another name. It's called the C statistic. Sometimes SAS is going to call it the C statistic, and I'll show you why that is a little bit, but it's the same thing. It's called the area under the curve. Okay, so if you're above 0.5, you're doing well. Your model has some value to it. It's able to, it's got some points where it's doing better than a coin toss, basically. And actually, you can get below that. That's really weird, where basically your model's like actively giving you wrong answers. This is where like it actually is telling you the opposite of the truth, rather than like the 0.5 line is the coin toss. Above it is like it's doing the right thing on average, and this is actually it's like you have a sinister model that always gives you the opposite of what you want. So that's in practice we don't see that. Frankly, it would involve like sinister models or something. So what's up? Is there with a model less than 0.5? I'm sorry. What? Oh, that's wrong. That's just like that. Thank you. We're used to that. There we go. Sorry. You know what I meant. Yeah, but you're right. So yeah, 0.5. So there's kind of some rules of thumb, because this is statistics and medicine, and both fields have rules of thumb. So what makes a good area under the curve? These are really rough guidelines. It really depends on which field you work in and what's considered good. Like really what's the standard of care and I use care broadly. What's the state of the art for what the field? And I'll explain what I mean by that. So, people say like if it's between 0.7 and 0.8, that's pretty good discrimination. That's a pretty good model. In the 80s, that's pretty good, even better, excellent discrimination. And above 0.9 is really rarely observed, frankly, and that's like fantastic discrimination. You have a point way up there in the corner where your model, you've got just the most amazing covariates in your model, and you're able to really predict the outcomes in your population very well. In truth, observational data is like complicated, and I mean, it's unlikely that in the 10 covariates in your model, you're going to be able to predict disease with such high accuracy, but it could be. I mean, it could be some disease states might be actually, described by a few very easy biological phenomena, and if they're in your model, you got it. What I will say, the state of the art for this in your field really matters. So I work in HIV prevention, and AUCs in the HIV world are always way above 0.9 because, let's say, looking at you're evaluating HIV testing criteria or diagnostics. You never really want to make a wrong call on an HIV test, either on the positive side or on the negative side. You want to falsely say someone's positive. You don't want to falsely. You want to incorrectly tell someone who's negative that they're positive. You never really want to make bad calls in either direction. And the state of the tests is so accurate that already things are way, way, way up in the left corner. And to get better than that, you need to have a super duper duper really good AUC to say better than in the current HIV testing diagnostics. So it's field specific. In general, for just regression models, this is a general guidelines. This may feel similar in a sense to another concept called the R-squared, which comes up in linear regression. Remember, the R-squared was also kind of about how much of the data are you kind of accurately kind of predicting and getting at with your model. It's the range of it's kind of a similar idea. And maybe you can almost say they're almost, I wouldn't say you could compare a 0.9 r squared to an AUC 0.9, but they're analogous ideas. And there's actually something called the pseudo r squared, which you can maybe compute from the likelihoods in your model, and it's down here. We don't really use it in this course, but that's another thing that people have used for logistic regression models to simulate the r squared, which is only a linear regression thing. AUCs are frankly much more used to evaluate logistic models rather than the r squared or the pseudo r squared. So, all right, how do we do all this? So first of all, how do we determine cut points? So maybe we have to figure out, how do we determine cut points? So in the examples that I showed earlier, we just made up numbers, 0.5, 0.25, 0.75, and whatnot. Those were completely arbitrary. Those were made up numbers. We said those felt like the right number of cut points. Those seem evenly spaced or whatever it is. And in that example, it seems nice. So that makes it easy to predetermine the cut points. And maybe, but it actually is not, we chose like 6 points. We made like 6 little tables or something. It made a very rough picture, right? It was a very coarse kind of thing that, so we didn't have to do that. You actually can make a smoother picture by using every cut point available to you in the data set. Okay? And that's what SAS is going to do. Okay? You can make a curve that's as smooth as the number of covariate patterns in your data set. Okay? So this is the covariate patterns G. That's every unique intersection of covariate values observed by your people in your data set. You're only going to get as many probabilities out of your model as combinations of x's that you have available to put into it. Okay, so remember the model, this ROC curve thing is built from predictions on the people in your data set. So you can only make as many cut points as combinations of the x variables available. So here we go. Here's some people. Here's an actual ROC curve that SAS would give you. Okay, this is the MRSA data set. So that example that we've been using, logistic regression. And if you ask it for, here's some model, I don't remember which model it is, with some x variables fit to the data set, and you asked it for an ROC curve, it can give you something like this. This has got way more points and smoothness to it than like me predetermining cut points of 0.5, 0.25, and whatnot. And what it's doing is it's using all of the covariate patterns to determine the cut point. So for example, you're someone who's had age this, previous hospitalization that, whatever. For that type of profile of a person, it can determine a cut point of, let's say that it predicted for you 0.3. We're going to now use the cut point of 0.3 for all the people in the data set. It uses all the cut points available as observed covariate patterns because it can't do more. This is as smooth as it's going to get. There's no more observations than this, and this is as many points as you're going to observe ever in an ROC curve. If you have 300 people, you can never have more than 300 cut points, basically, right? And so otherwise, there will be no new information to it. And so this is what it does. It's actually a smoother picture. It doesn't really matter whether you can predetermine 100 or you can use 300. You'll probably get to the same point, but this is the best that it will do. SAS is actually what computes this. This is what it will do. Here, what are these numbers? So this illustrates my point about it using the observations and their covariate patterns. This is showing the observation number associated with each cut point. So what I mean by that is let's look way up here. Here's 205. What it did, it went to observation 205 in the data set and said, hey, you've got antimicrobial exposure, you're a female, and your age is 26. I'm going to compute out of my logistic model for that profile of x's, your predicted probability is 0.9. You are going to have resistant staph. And it uses 0.9. At that intersection of covariates, it predicts a 0.9, and it makes a cut point who's above and below 0.9. And as you can see, or maybe it's actually the other way here, the sensitivity is 100%. This would be a low prediction. Sorry, it would be 0.01. Everyone's above 0.1. All the cases are above 0.01, basically. And the sensitivity is 100%. So when you see a point up here, it means it was actually a low cut point on probability. For person 205, it predicts really, really low probability. Everyone's above it, basically, is what this says. And it's using all the people. Here. You don't have to label it by the observations. This is kind of ugly. But this shows the process of how it computes these cut points. This is an ROC curve. SAS tells you area under the curve is 0.84. So actually, it's a pretty good model. It is able to pick up a lot of the, it correctly classifies, in a sense, a lot of the cases from the non-cases pretty well. So that's nice. We like that. So there's other ways to label the curve. Here we labeled it by the observations. But, what if you had a single X variable? This is a paper we did. It was evaluating a single X variable that was a score of it was a liver disease score as the X variable. Single X variable, okay? So, and it was nothing else in the model in this picture. And the outcome is whether is a surgical outcome on people getting liver surgery. And this is a score of how sick their liver was. Okay, so here's a score as the X variable, continuous X variable, and we're predicting surgical outcome. In this case, there's only one X variable. The number of cut points is directly mappable to the cut points of the scale, right? There's only as many covariate patterns as people's scores on the scale. So some people have, some people have a 12, some people have a 17, or whatever it is in here. In this case, you can actually label the graph by the X variable that resulted in that cut point, right? Every X, there's only one X variable. You put a 12 in for X, it predicts probability is 0.8, it uses that as the cut point. And here, you get to use the scale as the cut point, okay, as the labeling feature. The scale values as the labeling features. Why do I ever want to do this? Well, look at this. Here's 17. 17 is kind of the upper left corner of the ROC curve, more or less. This is not a very good ROC curve. It's not ever really achieving like area 1. But 17 is a magic cut point that does the best of this scale. It is the best value. If you were going to administer this scale if you were going to evaluate this liver disease score scale on a patient and you want to predict their clinical outcome, you would say, well, it's a 38 value scale. What's the right cut point for determining the surgical outcome? You would use a curve labeled by the scale values to determine, 17 is actually the best point at which to make the guess, right? That, above 17, you got a problem, and below you don't, or something like that. So you can label curves by all sorts of interesting things. Observations, the values of the X variables themselves, so which in this case is very useful for finding the right sweet spot of the evaluation scale. If you had multiple covariates, this would be really annoying because you'd have to label it by all the entire covariate pattern. They're a male with score 17 and their weight is this, and these would get really busy. I think you can do it, but it's going to get busy. So this is another cool thing you can do with ROC curves is actually scan and find that correct optimal point at which to make the determination of whose outcome is good and who's not. So how do you actually compute the ROC curves? The AUC curves, sorry. The AUC under the curve. There's two ways to do it. You actually compute the area by building a lot of little polygons under the curve. This is called the trapezoid rule. If you remember calculus, way back when, right, the way before you learn integrals, you learn computing area, like you compute lots of little trapezoids. People are shaking their head. Maybe you haven't taken calculus. Right, but you can basically, I'll show you a little illustration of this. Like you can, there you go, there it is, illustration. Right, you could compute, you can draw the curve and literally, SAS will do this for you. You don't have to do this. Compute all these little trapezoids, and then you can get the area under the curve. There's actually a faster way to do it, which is it uses the all possible case non-case pairs, and I'll show you what this means. It's on the next slide. So there's the long way and the short way. Here's the short way. What it does is it takes here's an example. Okay, we have a data set with 1,050 folks, 50 cases, 100 controls, non-case, 1,000 controls, non-cases. And what it does is you're going to look at every pair of case to non-case, all the possible permutations of, like, I pick one out of the 50 people out of a hat and one out of the 1,000, you pair them up. And you look at every pair of case and non-case, whether the case was predicted to have a higher probability of the outcome than the non-case, right? If your model's good, it's another way of summarizing what the ROC curve is kind of assessing. If the model's good, it's going to say that the case always that has a higher probability of the outcome than the non-case, right? So 0.7 versus 0.3, or whatever it's going to be. And if the model's perfect for any given pair of case and non-case, the case always wins. Okay, this is the basic idea, right? If the model is always if there's always this magic cut point where it perfectly splices the data, it's going to always predict, you know, the cases to have higher probability of disease than the non-case, and that's kind of what this formula kind of gets at, and here we go. So this formula is okay. This is where an ideal formula would look something like this. It's the number of, it's the proportion of all of the pairs in which the case was predicted to have a higher probability than the non-case, okay? These are ties. Sorry, I'm jumping over the specifics of the formula and just describing it. The W's are all the times when the case 1 had a higher predicted probability. In practice, we have ties where two people have the same covariate pattern, and the model says the same thing about both, and one's a case and one's not a case. So if you have two people with the same x variables, the model's going to say the same thing. It only knows the x variables. And so you get these ties, which are the z's, and the actual formula splits the ties. Okay, so this is what it does. So here's a situation where you had 50,000. There's 50,000 possible pairs of cases with non-cases, and if you saw that, let's just say 40,000. If anyone was nerd, there we go. It just gets smaller. Weird. So there's 40,000. 40,000 of the 50,000 pairs had a case where the case was predicted higher than the non-case. And then it splits 25 ties, and then it comes up with an area of 0.8. So this, like, heuristically makes sense as to what that it's evaluating kind of the discriminatory ability of the model. It actually always comes out exactly to the area under the curve. There's just a little bit of like magic here, where it actually perfectly is what the area under the ROC curve is. This formula is called C. It solves for something called C, which is what the C statistic is. And you've probably seen in the default proc logistic output, it gives you this thing called the classification table, and it says pairs concordant, pairs discordant, C. Have you seen that table? I think hopefully I have an image coming up. Do we have an image? Yeah, this. Okay, it's using this. I'm going to show you with an example, but it's giving you the pieces of the formula already to compute C. C is the area under the curve also, okay? So without even asking for an ROC curve, it gives you all of the components, the concordant, the discordant, and the tied, and you can compute the C statistic. So this is actually part of the default SAS output that it gives you. And so let's actually jump into an example. This is, can anyone read x-rays here? Anyone? You should have some physicians that might know it. Okay, this is I actually had this kind of fracture. This is a tibial plateau fracture. This is really uncomfortable. This is the top. This is your knee, and this is your tibia, which is the bottom bone, the bottom large bone that goes into your knee. And if you are going down a hill on a bike really fast and you skid out and you smash your leg, like some of us, you can get a tibial plateau fracture, which is really uncomfortable and totally ruins your summer. And it's when you basically slice off a chunk of your tibia, like the corner. This is a line here, This is like the tibia, kind of like the corner of it will get knocked off in a direction that's not comfortable. So it's a compression. It's a type of compression injury. Skiers, bicyclists, and so forth. So here's an example of knee fractures. This is not me. I wish I had my X-ray. I don't. So here's an example where we have 348 folks, and the idea here, the idea of this example is the outcome is fracture or no fracture. And imagine you're in a world where there's no X-rays, and all you have is this information. You have physical observations on the patient. Okay, you're dropped onto an island where there's no X-ray machines, but a lot of hurt people, a lot of bicycles, and the roads are hilly, and so there's all these people on the side of the road pointing at their leg, and you ask them some questions. Can you flex your knee? Can you put the weight on your knee? How old are you? You ask them some questions, and you maybe do some physical. You feel their leg, and you say, okay, it feels like the knee head feels injured, or whatever it is. You have some observations, but you don't have an X-ray, let's say. And you want to make a prediction, but behind the scenes there's someone far away who knows truth, and might have a hot air balloon-based X-ray machine, and they know whether there's true fracture or not, and we're assessing whether based on the physical observations, can we predict fracture status in the absence of imaging, let's say. And so you might fit a model that looks like this. You can say, hey, proc logistic, fit a model, fracture, yes, no, equals some covariates. And here's the physical observations on the data. There's some extra stuff here, right? There's some extra pieces. I'm going to show you this thing slash pprob 00 to 0.5 by 0.05 C table is asking for something that looks kind of like this. Actually, exactly like this. This is the 2x2 tables at each determined cut point. Okay, so here, look at that. This is not arranged in an optically nice way, but each of these 4 cells corresponds to the 2x2 tables that you would have made at that cut point defined as 0, and here it's showing it to just 0.5. And it's even telling you the basically kind of 5 things that you might measure on such a 2x2 table, right? Specificity, sensitivity, the other way around, sensitivity, specificity, false. This is the percent of false that are false positive, which is the positive predictive value. It's actually the 1 minus of the positive predictive value. This is basically the positive and negative predictive value. And this is the percent correct. So that's the diagonal. How many, it's just the percent correct. So things you might calculate, and here's the actual 2x2 table. So that's kind of neat. If I just gave you this, you actually would be able to kind of sketch out what an ROC curve would look like, right? If you can just do that based on this information alone. But we're not going to just stop there. We're actually going to do this. We're going to say plots equals ROC. And you can say ID equals OBS. Okay, so there's a whole bunch of options that SAS gives you for how you customize the plot. One of them is ID OBS. That is label it by the observation, right? That was this business of figuring out which person contributes to which cut point. So here's an example of the output, right? This just shows how to read it. You can see here that at a cut point of 0.1, 36 of 45 events were falsely called events. That's this, that should be that were actually called events, sorry. Let's see, 36 events, yeah, it should be truly called it. That's annoying. So 36 of the events were correctly called events. And here we incorrectly called, I'm reading this backwards now. This is the number of actual events. This is where SAS uses annoying lingo. It incorrectly said non-event, which means it was actually an event. This is SAS double negatives. That's why I was going, These are 9 cases that it incorrectly called non-cases. So therefore, they belong in the denominator as true events. And it should be that these were correctly called events. I'm sorry, this says the opposite. This is the number of true positives, and this is the sensitivity. 36 over 45. 36 over 45 equals 80. So I'm sorry, this should say true, and this is SAS This is SAS using double negatives. But you can use this to say 36 out of 45 total cases were called cases. That's sensitivity 80% and so forth. So you can use this to make the 2x2 table and write to SAS to change the language. That's kind of how you would read a row like this. So we got to change that to say truly. So here's what if that plots ROC business, which I actually don't have again here. It makes this. This is what SAS, this is if you don't say ID equals obs, actually. This is without the ID equals obs. This is just what it will give you by default if you just had the ROC option up there. And so you see here it gives you a plot. It's, again, with as many cut points basically as people in the data set. And you see area under the curve is 0.745. And that, by the way, was, 0.745. So it tells it to you over here, and it tells it to you in the default output without even asking for it. It will always give it to you. Here it is with the ID obs option. And again, here we go. And so here you're like, wait a minute. I see 376, 373. There's a lot of people in the data set. Where's all the other points? Where's all the other points? They're repeated covariate patterns. So like the other, it actually does look like it's omitting one or two, and maybe it's like a plotting weirdness. But there's only so many combinations, and it's not going to keep stamping the same ID over and over and over on itself. And so it's just choosing one. It's just choosing one. So here's how you compute the C statistic. Again, this is using the formula-based approach. So you can just trust SAS. That's 0.745, which is shown to you twice. Or you could use the percent concordant. What it means by concordant is that's lingo for the case the case had the higher probability than the non-case. It's calling that concordant. It's concordant with reality or something. I'm not sure. And discordant means it was the counterintuitive opposite of what you thought. The non-case was given the higher probability than the case. So discordant with that, truth or something. It's not consistent with what you'd expect. The discordant. And here's the ties, where two people, same covariates, same prediction, and so but one was a case and one was a non-case. They had the same X variables. They were called the same thing. That happened 5% of the time. And you can take this information and you have to manipulate it a little bit because this is the percent, and this formula uses the total. So you have to say 71.9 of the total. You have to kind of multiply it through to get to the formula is using the total number of folks, pairs, and this SAS output gives you pairs and then the percent of them. So you got to multiply it through to get the actual thing you want. But that's we can do that. We're okay with that. And then here is 0.7445. Also notice these cancels, so you don't have to listen to our formula. You can just use the output directly because this cancels. If you're feeling algebraically fancy, or you can just multiply through the number of pairs. So 0.7445 is the C statistic to even more precision than SAS will give you by default. So this is how you compute the area under the curve. But wait, there's more. So that was for a single model, but you can actually imagine, you want to, what if the name of the game was to find, you have 5 covariates. What if you want to find the best model where best is defined as like the model that like is the simplest and just predicts as good, like predicts best? What if all you needed was 3 of the covariates about the knee? What if you only needed 4? Right? How can I test whether I needed all 5 and I could have had a reduced model, not looking at the stuff we were looking at before, all of the confounding, what's the least confounding model that's the simplest and most precise and all that? What if you cared about prediction? What if I want to say like this, all I need to know is 3 covariates and that actually predicts knee fractures great? So there's a test, it's a non-parametric test that used to be a SAS macro and they actually got incorporated into SAS 9.3 and now 9.4. That actually is a test that SAS will give you to compare 2 ROC curves. And then you can use it as a selection technique. So here in that original paper that I showed with the liver scores, the point of the paper was actually to compare how two different scales compared to each other. It wasn't about the same one scale. It was saying we have two competing scales. Which one is junkier or not than the other? And so here's what we did. We actually overlaid two ROC curves. Here they are on the same patients. You have the same patients, and you gave them two competing models, basically. One that had the MELD score and one had the child score. But they're two models, and you wanted to say which model did better on the same data. Okay, so this is a little weird. It's like correlated in some sense. It's the same data, and you gave it two different models, and you want to say which one's better. And notice here, they're kind of the same. Right? 0.698 is one AUC we report, and the other is 0.755. Okay, so same-ish. And P equals 0.20. This is of a hypothesis test where the null hypothesis is they're basically performing the same. And the alternative hypothesis is there's a difference in the curves. And so from this, this statistical test is saying these curves are functionally kind of the same, no gain in prediction in one over the other. Okay, and so, and this, it doesn't really have the test doesn't have a name. You can call it the DeLong test maybe or something. I don't know if you want the D squared. I don't know. It doesn't have a cute name yet. But it's a test of correlated ROC curves. And they're correlated because it's repeatedly done on the same data. That's what they're saying that. And so you do this thing here. So I didn't tell you the whole truth before when I said SAS, to get an ROC curve, you have to specify this thing plots ROC. There's actually another way to get ROC curves. And this is actually, this is really cool. You can actually ask in one proc logistic. Here, this is a proc logistic that statement, it has a model of 5 things. You can say, give me an ROC curve based on a subset, a model that only had some of the covariates without refitting another proc logistic. Kind of cool. I don't know why they do this and don't allow other things like the likelihood ratio test, which actually makes you do several models. But this actually, so this statement, ROC flex HCAT, is from a model that's fracture equals flex and HCAT. And this is an ROC curve that is just that. And so here, notice the ROC, the AUC is 0.6648. That's lower. It was like 0.745. So I took some stuff out of the model, and the prediction gets worse. Okay, so that would make sense. The less information you have, it's just the prediction goes down. This is like in linear regression, R squared behaved the same way. The less that's in the model, the less good it is in predicting things. And the question is whether taking stuff out significantly makes it crummier, right? That's kind of the way the R squared test, that's what all of the linear regression tests were based on. When I take stuff out of the model, does it meaningfully get worse? And so here, the question is the 0.66 a statistically significantly lower AUC than the 0.745, let's say? Something like that. The gold standard model, let's say, is the full one, and it had a 0.745. So these two statements consider the following. It says, I'm going to consider a gold standard model that's got everyone, all 5. And here's 2 reduced models, one with flex, weight, and head, and then flex and HCAT. This is the label. And so I'm asking SAS here, give me the 2 plots. And then there's this other thing called ROC contrast reference model estimate. And it asks for this thing on the right. It's basically, here we go. It's going to give me all of this. It's going to first give me all the ROCs overlaid on top of each other. There's 3, because this thing says reference model. That means gold standard. Give me as the reference, the comparison group is the thing on the model statement. Okay, this is the unartful way of SAS. So it's saying the reference is this model with all 5, and it's giving me a plot with 3 curves. One that's called model, which is the one with all 5. There's 0.745. There it is. And here's the 2 reduced models on top of the other model. Okay, here's the plot. And then it gives me some other cool stuff. There we go. Okay, so here, you look at the bottom here. Okay, so First of all, it does this thing down here, which is basically kind of like almost like a chunk test. It's like saying, are any of them, is either of the two curves different from the gold standard curve? Like, is there any difference anywhere in the curves? Kind of like a very global kind of overview test. Are any of the three different? And then it gives you specific tests of the two reduced models versus the full. So flex weight head has a p-value of 0.6661. It's effectively no improvement over the gold standard model. So you can say, well, I can drop age and patellar, okay? So I can drop those because I have my reduced model, is basically giving me the same prediction as the full model. So these are like ideas. These are like likelihood ratio test, chunk test kind of ideas from before, but now we're applying it to ROC curves. Notice when I drop, this is actually a different model. In a model that had only flex and age cat, so it's just different covariates, but you can imagine it could have been one that dropped head only or something. In this reduced model, this one is significantly different from the full model with 0.01. So you'd say, whoa, this model stinks. And then that was the one that was 0.66 versus 0.74. So this was a statistically significant difference, but 0.7367, that's pretty close to 0.745. So the flex weight head was this value here. Okay, so now we have a way to do likelihood ratio test like stuff to our prediction approach of thinking about logistic regression. So this kind of completes, in some sense, like all the type of stuff we might want to know in doing our ROC type analysis. So to kind of bring it back together, goodness of fit was really about one model more or less fitting the average situation in the data, and the ROC is really like, can it predict people well? And you can use it to compare models using this kind of ROC contrast test here. And it's a chi-square test comparing the two models. So there's a whole bunch of extra slides here that we're not going to do because we want to go home. And it really marches through kind of some exceptions and illustrating where you have good discrimination and poor fit and poor discrimination and good fit, and really nails home this. This is like an intuitive heuristic thing that I was trying to talk about, but it really nails it home with a lot of examples and so forth. One last thing is there's this thing about separation of data points, which is when the data too perfectly fits into you split it too well. There's actually problems there's like a computer problem that happens. When your model is actually perfect, the computer doesn't like that. So you can't, and honestly, in life, this almost never happens where you can perfectly split the diseased and non-diseased. Life is complicated, it doesn't work that way. But if it does happen, SAS is going to give you a warning that says, warning, separation of data points has occurred. Where is it? I think we have a warning here. This. If you ever see this, it's because you have a covariate that perfectly predicts the outcome. All right, basically. It's kind of like collinearity, but collinearity was among the x variables, and now this is between your x's and your y. If you think about it, you have a perfect prediction, the model blows up, and that's called complete separation of data points. And so you will never, in practice, this almost never happens. It's kind of weird that perfect discrimination would be bad, right? Because it's kind of you want perfect, but too perfect actually will cause warnings and problems. And then there's so we're going to pick up next time with risk ratios and prevalence ratios. So there's another slide set, which we're just going to have as for reference on other diagnostic issues, which really rehashes a lot of linear regression concepts around outliers and leverage and all of that stuff, and just shows kind of how we measure that in logistic regression models. It's really for reference. There are concepts that you should think about, but we're not going to, I'd rather talk about risk ratios because that's more fun. So thank you.